Multi-threading is usually supported by thread libraries. Thread libraries can be either implemented on user level, so user level threads, libraries such as bthreads and window threads and Java threads, or kernel level libraries. And almost all modern operating systems have kernel level libraries to support multi-threading. You can go back to the reference and see the examples for yourself. For more convenient to software developers, the concept of implicit threading has been introduced because multi-threading is very popular, yet it's very hectic for a programmer to go into all the aspects of multi-threading in their programs. So implicit programming provides the programmer with a means of creating multi-threads without going into all the hectic details. This is implemented in three, and there are actually three examples here in the reference you might go and look into. These are thread pools and open MPs and grad central dispatches. There are other methods including Microsoft threading building blocks and Java Until concurrent packages. So all these are available for you either within the text within your reference or online to read about. What you will learn through life and especially through studying computing, that nothing comes without a price. While multi-threading is really of a huge value for programmers, users, and computer systems, yet it has its issues that we have to deal with and take into consideration. Many system calls were designed with a single process in head. And we will take one example here, that is forking an exe. Hardware has tasks like handling a signal that was also designed with one process in mind. Handling how a thread is terminated is another issue that we have to consider as operating system designers and application developers. What about the local storage, the part of the address space that belongs to the thread and other threads cannot access? How is it handled? And how does actually scheduling to take turns in the CPU happen? If we looked into these specific system calls, fork and exe, that we actually discussed before and we use to create processes. A process we'll use to create a child process. What if this system call was invoked by a thread? Will the thread be forking the whole process or will it be forking itself only? If it's forking the whole process, what about other threads? Unix, for example, has solved this with having two versions of fork. One that forks the whole process and another one that will fork only the thread that invokes the fork. And it totally depends on what is the purpose of creating this new process or new thread. while exe actually is executed the same, whether it was invoked by a process or a thread within a process. The code that it will call will replace the whole process in total disregard. What about signals? Usually, a signal will be sent to a process and will be handled by the process. Now, what if a signal was sent to a process with multiple threads? Which thread will handle the signal? That is a question for us as designers to answer. It's very easy to have a default handler, a thread that by default will handle all signals. Or to have a user-defined thread that will handle the signals. These are two options for us as designers to decide which one to be used. This depends on the task at hand. A question will be, okay, where should a signal be delivered for a multi-threaded process? It will be delivered to a thread which the signals applies. Means the signal is being sent according to certain criteria. So only the thread that fulfills these requirements will handle the signal, or it will be delivered to all threads within a process, or it will be delivered to a certain thread or group of threads according to what is preset, or a specific thread will be assigned of handling these signals. This is up to you as a designer to decide differently each time according to what tasks are being carried on. What will happen if a thread was terminated? That means it did not finish normally. It was aborted. This cancel thread we will call in the text the target thread. We have two general approaches. Either asynchronous cancellation that will terminate the target thread immediately, or deferred cancellation that allow the target thread to check every periodically whether it was cancelled or not. So it can end itself in an orderly way. If the thread was cancelled asynchronously, that means simply then the operating system should claim all the resources of that thread. If the thread was allowed to cancel itself, to terminate itself orderly, that means it will release the resources it has in a proper manner, better than canceling it immediately. Threads, as we have seen earlier in the illustration, had their own stack and their own data section. These storage spaces are handled by the thread, and we call it the thread local storage. It's useful when you don't have actually control over the thread creation. The processes create their own threads. And these spaces are different from the local variables within the functions. Let us look at them as global variables for threads only. That means all the functions that is running within the thread can access this space, whereas other threads cannot access this space. This is an issue to be managed by the memory management system and to be considered in designing your memory management system as an operating system designer. Scheduling threads within a process is another issue because we usually look at a process and we schedule a process. Like having multiple threads within of execution within at the same process, uh, that adds another dimension for the scheduling algorithm. Whether we're considering multiple to multiple scheduling model or two-level thread model, we are talking here about multiple user threads mapped to multiple kernel threads. And here, the introduction of a lightweight process that I've mentioned earlier that works as a multiplexer is very useful. It will work as if it is a virtual processor where it will work on mapping the user level threads to the kernel level threads, scheduling them to be scheduled to the CPU. Like when they need two-level scheduling. There are two examples for operating system threads in the textbook I would like you to go and look into, but all the reading parts of this chapter are not included in your final examination or in your midterms. Thank you.